Chemistry 0620 Cambridge IGCSE. Topic 1 States of Matter. So, just to clarify, this is an introduction video to the beginning of a new series, which is the Cambridge IGCSE Chemistry 0620 series, where we'll try to cover all the topics of Chemistry 0620. So, let's start with the first topic States of Matter. So let's define chemistry. What is chemistry? First, I want you to ask yourself, what do you know about chemistry and how do you define chemistry? After you thought of your answer, let's define chemistry according to a syllabus. It is the study of how matter behaves and how one kind of substance can be changed into another. So we're going to study how matter behaves in chemistry. This is the simplest definition you can get, I guess. I mean, it's the study of how matter behaves. Matter is anything that has mass and volume. Mass is the amount of matter present in an object. Volume is the space occupied by an object. So there are many different kinds of matter, and samples of all of them occupy space, volume, and have a mass. So we are going to be studying three chemical substances that exist in nature. These three substances are states of matter. So there are three states of matter in our syllabus: solid, liquid, and gas. Okay? The existence of each one can be altered by changes in pressure and temperature. So up till now we have understood the definition of chemistry, study of how matter behaves. Matter is anything that has mass and volume. Matter can exist in three different states: solid, liquid, and gas. Coming to the next definition, fluidity. What is fluidity? Fluidity is the ability to flow. So, the ability for a substance to flow, like gases and liquids. According to the particle arrangement, gases and liquids are able to flow. Solids are rigid, they have a rigid arrangement, so solids are not able to flow. Liquids and gases are fluids because they can be poured or pumped from one container to another. Solids are not fluids. Properties of states of matter. So we're going to be studying the following properties of each of the states of matter: shape, volume, density, fluidity, particle arrangement, and particle movement. Solids have a definite shape. Their shape is fixed. Okay. Liquids have an indefinite shape. They take the shape of their container. When you pour a liquid inside the container, the liquid is going to take the shape of that container. Gas have an indefinite shape. They also take the shape of the container. But solids, because and due to their particle arrangement, they have a fixed shape. Volume. Solids have a fixed volume. For example, this pencil. This pencil is a solid. It has a fixed volume. Liquids also have a definite volume. Gases have an indefinite volume. Density. Solids have a high density, liquids have a medium density, and gas have a low density. Fluidity, as we said, solids are not fluids because solid cannot be pumped or pushed from one container to another. Liquids and gases are fluids because they can be pumped and pushed from container to container. Particle arrangement. Solids have a regular pattern, liquids and gases are randomly arranged. Particle movement. Solid particles vibrate in their position, liquid particles slide past each other, and gas particles are moving in random direction. The movement of gas particles is also known as Brownian motion. So, structures of three states: the solid are packed together with low energy, high density. Liquids have medium energy, particles are sliding past each other, and they have a medium density. Gases have the highest energy and the lowest density. Gas particles are moving in Brownian motion, random directions, or in a zigzag pattern. State changes. So, matter can change between solid to liquid to gas or gas to liquid to solid. Okay, so these changes, approximately, we have 6 main changes that occur between these three states of matter. Okay, during these three changes or three states of matter, during the state changes, what happens is that usually there's an increase in volume when the temperature increases, and there's a decrease in the volume when the temperature decreases. We're going to come to this point in more detail when we talk about the relationship in gases between pressure, temperature, and volume. So the first change of state is from solid to liquid. Solid to liquid is like melting. For example, you have a solid ice cube, you keep it in heat. What's going to happen is after some time, this solid ice cube is going to melt. Why? Because heat energy was applied to it, causing the particle arrangement, causing the strong bonds in the solid to move faster and break the energy holding them together and move away slightly past from each other to become into a liquid. This requires heat energy and occurs at a specific temperature known as the melting point. Boiling is the opposite of melting. It requires heat energy. During boiling, bubbles are produced, okay, below the gas level surface and rise up to the surface. It occurs also at a specific temperature known as the boiling point. Freezing. Freezing is from liquid to solid, okay? Freezing is the reverse of melting and it occurs at the same temperature as melting, which is known as a freezing point. Melting point and freezing point of a pure substance are the same, example water. It requires a decrease in temperature, which is the thermal energy, and it occurs at a specific temperature. Then we have condensation. Condensation is going from gas to a liquid. This occurs by cooling. It takes place over a range of temperatures, so condensation doesn't occur at a specific temperature. So as a gas is becoming a liquid, the gas is cooled and the particles lose this energy. This is they do not have enough energy to bump into each other. They lack energy to bounce back every time, so instead they just choose to group themselves together and slide past each other, eventually becoming into a liquid. Sublimation, solid to gas, only occurs in a few solids like iodine or solid carbon dioxide. Evaporation is also liquid to gas, just like boiling, but evaporation can occur over a range of temperatures and there are no bubbles present in evaporation. Okay, it occurs at the surface of the liquids where only the high energy particles are escaping the liquid surface. So this is it summarized. State changes. Okay, solid to liquid is melting, liquid to gas is evaporation. Again, evaporation does not require bubbles. It is only escaping of the high energy particles from the liquid surface. Gas to liquid condensation, liquid to solid freezing. So any change from solid to liquid and liquid to gas needs heat energy. Any change from gas to liquid and liquid to solid gives out heat energy. Any change that gives out heat energy is an exothermic change. Any change that needs heat energy is an endothermic change. Evaporation versus boiling. Evaporation occurs at the surface particles, allowing the high energy particles to escape the surface of the liquid, and it occurs at any temperature. Boiling occurs at a specific temperature known as the boiling point. Occurs when a liquid is completely changed into a gas. Pressure and volume inversely proportional. We'll come to this later in depth. Volatility is the property of how easily a liquid evaporates. Volatile is a liquid that evaporates easily. So any liquid that evaporates fast is a volatile liquid. Okay, for example, water has a boiling point of 100 degrees Celsius, ethanol is 78. So which one boils faster? Ethanol. So this means ethanol is more volatile than water, or ethanol has a higher volatility range than water. Why? Because it evaporates faster. The relationship between boiling point and atmospheric pressure is that if the atmospheric pressure is decreased, the boiling point will increase. And if the atmospheric pressure increases, the boiling point increases. So it is directly proportional. Okay. Pure substance. Pure substance is a substance containing only one type of particle. This one type of particle can be atom, ion, molecule, but any substance that contains only one type of particle is a pure substance. Now, pure substance can exist in two forms. It can either exist as an element or it can exist as a compound. An element is a pure substance only containing one type of atom of a singular element. A compound is, in simple terms, two or more elements chemically bonded together, and compounds are chemically bonded. They can be separated by chemical means. Elements cannot be separated by chemical means. So let's have a look at some type of elements. We have the single atomic element that contains only one type of atom and it is not chemically bonded, like argon, neon, krypton, sodium, etc. Two atom or the diatomic elements, these are very important throughout your whole syllabus in chemistry 0620. So the seven diatomic are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So the last four are your halogens, and then we have hydrogen, nitrogen, oxygen. Triple or three atomic elements, example ozone, O3. Quadratic atomic elements like P4, phosphorus. Atomic element like, 8 atomic element like S8, sulfur. Okay. Now let's have a look at some key facts. The melting point and boiling point of a pure substance is used to test the purity of a sample. Okay. Impure substance. Impure substance is a substance containing two or more different atoms of different elements not bonded chemically. It can be element or compound. So it is a substance containing two or more different types of particles which are not chemically bonded. It can either be a mixture of elements or a mixture of compounds. As you can see, two different type of particles not chemically bonded. Here also two different compounds not chemically bonded. Pure substance melts and boils at different temperatures, while impure substance melts and boils over a range of temperatures. Kinetic particle theory is a theory which accounts for the properties of the three states of matter in terms of the movement of particles that can exist as atoms or molecules. So, this theory explains what happens during the changes of state, whether you're melting, boiling, condensing, or evaporating. So particles are obviously moving all the time. Particles are never stopping in motion. And of course, the higher the temperature, the higher the average kinetic energy of these particles. So the higher the rate of speed of the particles. And the movement of arrangement is different for all three states. Of course, gases have the most freedom and movement in terms of particles. So this is why gases are highly affected by changes in temperature and pressure. Now, how does the kinetic theory affect the physical changes? When the temperature of a solid is raised, the particles occupy more space and vibrate more and expand. Eventually, they will have enough energy to break through the bonds on the forces holding them together, and they will initiate to melt. Boiling or evaporation is almost the same concept. Basically, as you're heating it, eventually it will be heating up so much that it's going to break the attractive forces holding the structure together and eventually become a gas. Pressure, temperature, and volume in gas. So how does change in temperature affect volume, and how does change in pressure affect volume? Rule is very simple. Temperature and volume is directly proportional. Increase the volume, increase the temperature. Decrease the volume, decrease the temperature. And pressure and volume is inversely proportional. Increase the volume, decrease the pressure. Decrease the volume, increase the pressure. Why? Because let's say you have a container, okay, and if you are increasing the pressure inside a container by placing a piston inside it, the volume is decreasing. As you're taking out the piston of this container, the volume is gradually increasing. I hope that is clear. The main point you have to remember: temperature gas directly, pressure gas inversely. Now, intermolecular space is the space between particles like atoms or molecules. Because the intermolecular space between moving particles in a gas is greater than the other two states, this is why they are affected so widely by the changes in temperature and pressure. As you can see, increase in temperature increases the kinetic energy. Increasing the kinetic energy will mean they move faster. So this means eventually it's going to increase the volume of the container. If the container gets bigger, volume increases, so gas pressure decreases, but the temperature increases. If the container gets smaller, then the volume has decreased, but the temperature has also decreased, and the gas pressure has increased. More gas pressure, less collision. More collisions is less gas pressure. So this is the example I was trying to refer to here. If you have a container, as you're increasing the pressure, you're decreasing the volume. If you pull this back up, see, as you pull it back up, the volume has increased. Heating curves and cooling curves, which is going to be our last part for the first topic of Chemistry 0620. Heating curve is basically a curve that shows how these states are changed in an endothermic manner from melting to boiling to evaporation. So of course you start with an ice solid in the beginning, then as you're heating the ice until you reach the melting point where it begins to melt. During melting, the temperature change is zero. There is no temperature change until the substance has completed melting. After that, the temperature begins to rise again until it reaches the boiling point where the temperature is constant and the substance changes from a liquid to a gas. After that, it continues to increase to once reach a point where everything is converted into gas. Now, heating with the solid causes the particles to expand more until it can break the forces holding it together and eventually become a liquid. Heating the liquid causes the particles to expand more and overcome the attractive forces holding it together and sliding past each other, allowing it to become a gas. Why does temperature stays constant during a heating curve? Why? Because all of this energy that you're using to convert these states from one to another, this energy is being used to break the bonds holding the structure together, allowing it to change from one state to another. So this is why temperature during the heating curve stays constant, because all the energy is being used to change the state from one state to another. Heating curve, like I said, is an endothermic change, so it has a delta H negative value. Enthalpy change is negative. Cooling curve is the exact opposite of the heating curve. Okay, so basically take the heating curve and reverse it. What's gonna happen? You're gonna start off with a gas, the gas is gonna condense to a liquid, and the liquid is gonna freeze to a solid. Again, during the change of state, temperature always stays constant. Why? Because all the energy is being used to bring the bonds closer or break apart the bonds to change the state from one state to another. Temperature during the cooling curve, like I said, it's constant. Cooling curve, if it's the opposite of heating curve, and if heating curve is a negative enthalpy endothermic, that means cooling curve is an exothermic positive enthalpy change. And that is going to be all for the first topic of Chemistry 0620 Cambridge IGCSE. Any questions, feel free to ask me in the comments below.